so this is the list of what we've been through during the last classes, when we considered all the effects that are relevant affecting an electromagnetic wave crossing a region with plasma, and also possibly with some external magnetic field, as well as the latest effect we've seen. So the scattering, and the scattering caused in the propagation of the electromagnetic field, of the electromagnetic wave through a region characterized by irregularities in the plasma density, which correspond to a change, random changes in the refractive index. So let's see a fair example of all these effects about a topic which has become one of the hottest ones in the current research in astrophysics, which are fast radio bursts, which are just shortened as FRBs. So what are they? We don't know, essentially. That's the answer. Well, as the name suggests, these are just a burst, so very brief emission of electromagnetic radiation, which are typically observed in the radio bands, so around 1 gigahertz, but then can be, some of them have been observed also at several megahertz, 100 megahertz, sorry, frequency. So of course, well above the plasma frequency of the ionosphere. Otherwise, you couldn't see them. And essentially, they are fast in the sense that they last just a few milliseconds, so very, very short. And as a matter of fact, a lot of progress has been done, and I will just mention in the following slides. This is a relatively novel phenomenon. It has been discovered in 2007, so a little more than 10 years. But a lot of progress has been done recently, particularly the last year. And as I said, it's been attracting a lot of interest, a lot of attention, much attention in the latest years, and a lot of experiments have been built and are planned to be set up in the future, just to understand what they are. One of the characteristics that you immediately pick up about these events is that they are characterized by a relatively large dispersion measure. So in particular here, you see in this plot here, these are all light curves. So the flux is a function of time. Time is the horizontal axis. Here and from bottom to top, you see an increasing frequency at which you observe the signal. So immediately you see that at the lowest frequency, the lower the frequency, the later the pulse. You see all these squares just highlight where the pulse is. So so there is a dispersion, and indeed, if you work out the delay, so the arrival time as a function of frequency, you indeed find the 1/nu square scaling. And if you remember, that's exactly what we expect in the case of an electromagnetic wave crossing a region with plasma, with cold plasma. So in particular, the scaling is 1/nu square, where nu is the frequency at which a given pulse is observed, and the proportionality constant is the so-called dispersion measure. So is the amount of plasma integrated along the line of sight. So by measuring the delay, so by measuring kind of slope, which I here denoted as with this arrow, you weigh the amount of plasma along the line of sight. And okay, this is on the left here is just a picture of the same concept. So with blue, you mean higher frequency all the way down to red, which is of course lower frequency. So the beginning where the FRB source is, whatever it is, you have essentially the same pulse, just has the same timing, so the same for all frequencies. And then as the waves travel along the regions between the source and the observer, and so by crossing these regions, they just go through some plasma. So then there is a delay, so higher frequency lag, and just lead and lower frequency lag behind. And the amount of the delay, of course, scales proportionally with the dispersion measure as we defined it. You might want, something that I didn't tell you yet, but I'll show you a fair example of this. These pulses, these bursts, are very bright in the radio band, very bright. So one might wonder why it took so long to discover them. The reason is that, you see, when you are looking for some transient events in your data, if you sum up at the same time, of course, all the frequencies, there's no way you can see them because you sum up this pulse and then here you have nothing. So essentially the statistical noise that then just takes over. So this is just washed out by the noise. The only way is just you have to figure out to assume a given dispersion measure, so sum up in such a way that all these pulses are just increase the signal to noise. In that case, you can see that. But in principle, beforehand, you don't know exactly the amount of dispersion measure. So you don't know how to shift in time all the different profiles so as to have all the different pulses just summing up aligned in time. So in principle, the search for these events have to be conceived properly. It's not so trivial, even if they're really bright. So that's one of the reasons why it took so long for scientists to find them out. And one thing which immediately stood out as soon as they discovered them is that if you compare the dispersion measure, and you compare it with what you would expect from our own galaxy. I remind you, we are living within our own galaxy. So for any possible line of sight, you have all the plasma belonging to our own galaxy, so just a few kiloparsec away from us, which we know very well because we studied it through all the many pulsars that lie close to any line of sight. So our pulsars, so these stars, which are very good sources of radio pulses, but which live in our own galaxy, we exploited them to map all the amount of plasma due to our own galaxy for any possible line of sight. So for a given direction, let's suppose you observe a given fast rate of burst. You observe one fast rate of burst, you know more or less the direction. So you know also the amount of dispersion measure that you would expect for that specific line of sight in the case of a source which lives within our own galaxy. And what they immediately found is that the dispersion measure measured for the fast rate of burst was significantly higher than the highest possible dispersion measure for that line of sight due to our galaxy. So this was immediately taken as a possible hint for an extra galactic origin. So the source of FRBs might belong to our faraway galaxy, not to our own galaxy. I'll get back to it in a few slides. So, but let's see an example, data about events. So this is the so-called typical dynamic spectrum. So what is that? In the x-axis you have time. In the y-axis you have frequency, observation frequency. So again, you see this thin, darker line is just the arrival of the pulse as a function of frequency. So again, something that I already told you last time, if you focus on one specific frequency and you go through a horizontal line, you see the signal as a function of, so it's a color-coded. So the darker, in this case, and the stronger the signal, the higher the flux. So you see, for example, here you see nothing, and then at this point you have the pulse here. So you clearly see that the arrival time increases with correspondingly lower frequency. And indeed, this pattern is 1 over nu squared. So indeed, this is fully compatible with a delay, temporal delay, that you would expect from the dispersion measure of the plasma along the line of sight. So by measuring this line here, essentially you measure the dispersion measure. And here you see in this inset panel here, you see the pulse profile. So flux is a function of time at 3 different frequencies. You immediately, they have been aligned. Okay, of course, this guy comes later, but they have been aligned just to let the reader, in our case, ourselves, to appreciate the difference in the shape, in the temporal shape. And you immediately see that the higher the frequency here, and the narrower the pulse. And indeed, this is reflecting the scattering time. If you remember, the scattering time scales in the simple picture that we've gone through in the last class as 1 over nu squared, nu to the 4th power, sorry. So indeed, you would expect that the same pulse, not only is a given pulse delayed at lower frequency, but at lower frequency it's also broader. Its time profile is also broader because of scattering. Okay, so who's responsible for scattering? Well, the plasma that lies along the line of sight. But I'll comment again this in a moment. This is another example, the same kind of plot. And in addition, so here the color one is just a dynamic plot. So again, frequency as a function of time. This is one of the brightest ever measured fast radio burst. And it is one of the first also to be discovered. And one might also argue that it took one of the brightest to make people realize that they were facing a brand new phenomenon. And indeed, that's also called sometimes discovery bias. So until you find, let's suppose there is some class of sources that you are not yet aware of, you in the end, you recognize them as a new class compared with other classes that you already know of. You find them out, and only when the event due to this new class is so bright that there's no way you can miss it. So in this case here, the naming convention, you see all these digits, is fairly simple. 01, the first 2 digits refer to the year of discovery, so 2001 essentially. 07 is the month, so July, and 24. So this FRB was discovered on July the 24th of 2001, so 19 years ago. And it's called Rory burst after the name of the first scientist who published it. And this is one of the bright. So you immediately see here from the color-coded plot that the signal was really bright. It was so bright it saturated the receiver of the Parkes radio telescope, which was one of the first radio telescopes, which is in Australia, by the way. which was one of the first radio telescopes who, well, the one which essentially discovered the phenomenon of fast radio bursts. It was so bright that just saturated the receiver. This is just the flux, which just that went back to a different level just because of that. So bright, so incredibly bright. Several, in this case, 100 Jansky, if I remember correctly. So again, this is just to show you what's the effect of the pulse broadening due to the scattering of the plasma itself. So again, this is the same result we obtained last time. So with tau c is just the scattering time. So how essentially the emitted pulse that you see here from the source. So if you could stay very close to the source, you would see something like this. But unfortunately, well, fortunately, it's just a way of putting it. The wave has to cross along its path some region filled up with plasma irregularities, as I told you. So with variance in the plasma density. So this causes some broadening in addition to dispersion measure, also broadening of the pulse. And that's the reason why in the end you measure a pulse whose time profile looks like this. So it got broadened just because of plasma scattering. And I remind you that, well, in addition to the 1/nu⁴ scaling with frequency, so it's strongly dependent on frequency. So the lower the frequency and the much broader the profile. Here R and R prime are just the distance, the mutual distance between source and screen and observer. So in particular here, you see that this ratio, as I told you, for a fixed distance between source and observer, so fixing R plus R prime, this is maximum when essentially the screen lie more or less in between. And okay, this is just something. Here in this plot, you see the scattering time. This is something that you measure by measuring the broadening of the pulse as a function of the dispersion measure. And essentially what was found for the pulsars here, so the shaded gray line, the gray region here, is the region where the galactic pulsar, so sources which belong to our own galaxy, lie. And in particular, you see that there is a given dependence, so there is a relation between the two quantities. And this is due essentially to the properties of the galactic plasma, because of course the sources are mostly affected by it, belonging to our own plasma. And in particular, as I showed here by this formula, and I was commenting just before, in determining, in shaping the scattering, so the broadening of the pulse, what is most relevant is the amount of plasma that lie in between the source and the radio telescope and the observer. Unlike the dispersion measure, if you think of the dispersion measure is just an integral of all the plasma lying in between, with no difference on whether the plasma lies closer to the source or to the observer or in between. Well, in determining, and this is different from what happens in the case of the broadening due to the scattering of the plasma, because in this case, if the screen is, if you consider a number of different screens, as realistically is the case, their contribution to scattering is not the same, because those screens which lie either close to the source or relatively close to the observer have a much smaller impact. The ones that have a stronger impact are the ones which lie more or less around the middle point between the two, so in the middle. And so because of the properties of the plasma, I was saying, so the galactic sources just are lying in this plot here, lies in this region. And these 3 points, this is one of the earliest plots, which at the time when a few fast radio bursts had been measured. So they immediately saw that these are upper limits. So the upside down triangles are upper limit. So you don't measure, but you surely are below this value. So they immediately saw that these sources didn't follow the typical relation between the scattering time and the dispersion measure followed by the galactic sources for a given dispersion measure. And in the hindsight, we know that, as I will tell you in a moment, now we know that all these sources are extragalactic sources. So extragalactic sources means that what mostly affects the scattering is what lies in between. But what lies in between us and an extragalactic sources means something well outside the galaxy. So something which has different properties from the galactic plasma. So that explains. And that was a hint that was already taken at the time as a hint, as a further hint for a non-galactic origin of these events. So this is just a collection of light curves. By light curves, I mean flux as a function of time. Because of the dispersion measure effect, of course, these have been integrated in a given frequency band, but in order to enhance the signal, you have to correct for the dispersion measure, so to align temporally the same peaks as seen at different frequencies. So as when I was talking, I was mentioning as an example of dispersion measure the pulses produced by the Crab Nebula, which is a galactic source, of course. I told you at the time that the dispersed profile, so corrected for the dispersion measure. In this plot, you see the analogous ones. So all these pulses have been dispersed, so they have been corrected for the dispersion measure, just to appreciate the shape. So with the name again on the left, on the top left of each of them, you see the name. So in this case, for example, 150215 means February the 15th of 2015, just to let you know. And so you see some variety. Some are really, really bright, like in this case, also here, the one that I also measured. But they're not all alike, in the sense that if you have an exquisite time resolution, you see here time is in milliseconds, and frequency, so they are all dynamic plots, which have been corrected, which have been dispersed. So they have been shifted in time to correct. As here you see the overall dispersed profile. So in some case, you see that it's not just one pulse. There can have complex substructures. So is this telling us that there is a different population of FRB sources? So what are these sources? We just have some hints that I'll briefly mention, but essentially we don't know. How many fast radio bursts do we observe daily? Well, that's an estimate that has been done through different surveys, so through different studies. Essentially, you have to consider that, particularly at the beginning of so kind of 10 years ago, because now things have changed. But at the time of discovery, so kind of 10 years ago, as I was saying, the field of view, so the portion of the sky that was monitored by this radio telescope was relatively small. Typical regions whose size were just below much smaller than a square degree. So very small, relatively small region of the sky. So correcting for that, when you correct for the, when you account for the amount of the size of the region that were monitored, and you correct and you calculate the rate of fast radio bursts through the entire sky, so number of FRBs per day, coming just from the entire sky, you see some kind of different numbers, because it depends also on the sensitivity of your instrument. If your instrument is capable of seeing very faint events, then you are expected to see more of them. If you are just sensitive to the brightest one, then correspondingly fewer. So this is just a table in which the limit fluence, so the fluence is energy per unit time, per unit area, per unit frequency. So it can be measured as flux density times time. So Jansky times millisecond, which are typical units. This is the frequency at which they have been observed. So all of them, in this case, 1.4 gigahertz. And the C, clearly, the lower this number and the more sensitive the surge. But essentially, the astonishing number is that it ranges between several thousand up to more or less 10 to 4, so 10,000s. What is this? Well, this is the rate of FRBs that you get from the entire sky each day. So several thousands at the very least. So there are a lot, in just a lot of them. So it's really, again, one might wonder, how is it possible that you've got a phenomenon which is, you've got thousands of them per day, they're relatively bright, and you just, and they have been discovered only recently. Again, because of it's the combination of the reasons that I was telling you about, the difficulty of searching for them, combined with the relatively small field of view of the radio telescope. So even if there are a lot of them, but if you just monitor a relatively small portion of the sky, of course you are not expected to see plenty of them. And then people realized that it was worth building radio telescopes that were capable of monitoring much wider regions of the sky. So in the end, nowadays, there are some experiments which can measure more of them. I'm not going to the technical details of what are the properties of the radio telescopes in order to measure. There's kind of also trade-off with the capability of localizing them. But this is something that I'll touch upon briefly later. What is this figure? Well, this figure is just a scatter plot. So you have two variables. On the x-axis, you have the dispersion measure, parsec times over centimeter cube. So the dispersion measure that we know. And in the y-axis, you have still the dispersion measure, but in different units, divided by the maximum dispersion measure that you would expect. This is just NE 2001 is just a model of the plasma density in our own galaxy as a function of the direction. So it's a function of the line of sight. So this is for any, so this ratio, so this is just a dimensionless ratio between two different dispersion measures. So the dispersion measure of any single objects that you consider over the maximum dispersion measure that you would expect due to our own galaxy for that specific line of sight. So for the specific direction that you are at which you are observing the events. So essentially, all the red points here are galactic objects. So galactic objects, it's essentially pulsars. And you immediately see that this solid line here, solid horizontal line, is just the value of 1. So it means that you immediately see that essentially all of the red points lie below this line. And indeed, this is something to be expected. Why? Because since they belong to our own galaxy, of course, depending on how close or how far, if you want, along the line of sight they lie from us, the dispersion measure will be either small or much smaller or comparable or at the maximum in the extreme case when they lie on the other side of the galaxy. Well, the dispersion measure you measure is just close to the maximum dispersion measure because the line of sight in that case is crossing all the galaxy for that specific line of sight. And these kind of red diamonds that you see here, these actually do not belong to our own galaxy, but they belong to our satellite galaxies. So the Magellanic Clouds, small SMC stands for Small Magellanic Cloud, and LMC for Large Magellanic Clouds, which are galaxies, small galaxies, which are close to our own galaxy. Because so they are extragalactic objects in the sense that they do not belong to our own galaxy, but they lie essentially relatively close to us. So the excess of the dispersion measure with respect to the maximum that you would expect, so they lie above, but not so much. Because essentially, since they belong to our other galaxies, so to the Magellanic Clouds, what contributes to the dispersion measure is also the portion of plasma which lie along the line of sight and belong to the Magellanic Clouds. While the blue stars, they are all fast radar bursts. So you see that the dispersion measure that you get for a fast radar burst is significantly larger than the maximum dispersion measure you would expect due to our own galaxy. And by how much? Well, you see, even a factor of 10 up to 100. So it means 10 times, 100 times more plasma than you would expect in the highest, in the extreme case of one object just lying on the other side of the galaxy. So this was immediately pointing to an extragalactic origin. And indeed, assuming that there are some models in which you can assume the density of the plasma in the intergalactic medium, which is the acronym here IgM stands for intergalactic medium. So let's suppose that the wave is indeed, the electromagnetic wave is indeed due to a source which lie far away from our own galaxy. So it means that the wave has to, in traveling to us, has to cross most of the path just lie in the intergalactic medium. So in the medium between the galaxy to which the source belongs and our own galaxy. So assuming some densities, and there are models based on the evolution of the universe and also partially based on observations, in which you can measure the density. So essentially you can obtain a curve, a relation between the dispersion measure due to the intergalactic medium and the distance. Distance here is measured in terms of the source redshift. The redshift here, as a reminder, as I told you in probably the first class, it's the cosmological redshift, the one connected with the universe expansion. So it's a way of measuring distance. And in particular, you see in this example, if you measure dispersion measure, sorry for that, but of 1,000 parsec per cubic centimeter, and this is entirely due to the intergalactic medium. In this case, you see that by measuring a dispersion measure, and if you can ascribe it to the intergalactic medium, then essentially you have a handle on how long the path along the intergalactic medium has to be to yield this value. So this turns into a range on the possible distance, or equivalently on the possible redshift. So this turns into a redshift range, where the range is because of the uncertainties affecting this relation, and also on the randomness, because the plasma in the galactic medium has some variance, is not homogeneous. The density can vary. So considering all this, you have a range. So you might end up with the same value for the dispersion measure entirely due to the intergalactic medium within a range of redshift, so within a range of distance. So you immediately see that by measuring the dispersion measure, or should I say the excess dispersion measure. What is the excess dispersion measure? Is the dispersion measure that you measure in addition to the ones to the contribution of our own galaxy. So is the excess the dispersion measure which is in excess of the value that you would expect from due to our own galaxy. If you then ascribe it to the intergalactic medium, this is a way of estimating with some due uncertainty the distance. So the higher the dispersion measure in excess of the galactic value, and the correspondingly larger and the correspondingly further away the source is. Another interesting aspect is the brightness temperature of fast radio bursts, which is potentially telling us about the nature of the process, in particular, whether it is a coherent or incoherent process. How can we do that? Well, let's see the definition of brightness temperature. If you remember, just starting from the black body law in the Rayleigh-Jeans regime, so the specific intensity is just this one here. And so this is exploited in the definition of brightness temperature. So you define, by definition, brightness temperature for any generic measured specific intensity by just inverting this relation. So the brightness temperature is, by definition, associated to a generic intensity. Specific intensity is just this I, so the specific intensity times c squared over 2k nu squared. Definition of brightness temperature. What is the specific intensity? Well, let's suppose from a very practical point of view that you measure, what you measure essentially is a flux density. What I call S nu here is a flux density. So energy per unit area, per unit time, per unit frequency. Okay. Well, you measure, for example, in Jansky from the point of view of units of measure. Over what? Well, this is, I remind you, the specific intensity is flux density over also per unit solid angle. In this case, it means that if I measure from a given source a flux density S nu, I have to divide, if I want to calculate the specific intensity, I have to divide by the angular size of the source itself, which I call here capital omega S. So capital omega S is just the solid angle subtended by the source of radiation, from my point of view as an observer. How can I estimate this? Because in many cases, as for example in the case of FRBs, I cannot resolve. So the resolving power of my radio telescope is much larger than the angular size of the source. So there's no way I can measure this guy directly. But I can exploit some properties. In particular, let's assume we know the distance between us and the source, and capital D is distance. Well, by definition, if you want of solid angle subtended by a given source, by a given source of radiation of size, of a given size, of a given area, is just the area divided by distance squared. And that's exactly what I did here. And if you look at the quantity among brackets, here is the linear size of the source. But what is C? Well, C is the speed of light. And what is W? Well, W is the temporal width, so the duration of a pulse produced by the source. So C times W, so C times the duration of the pulse, is telling me about the linear source. Why? Because I'm exploiting if you remember, if I have a source which is causal connected, and then this source undergoes some flux change, well, no matter about the about, well, the duration of the pulse that I observe cannot be smaller than the speed of light. The speed of light times well, the size of the source over the speed of light. So it means that I can estimate the source size by multiplying the speed of light times W, so times the duration of the pulse. Okay, so this is not a precise estimate, but is telling me an order of magnitude estimate of the extension of the the size of the source. Okay, so if the source emits pulses which cannot be shorter than a few milliseconds in the specific case of fast data burst, so W would be just a few milliseconds, so 10 to minus 3 seconds. So it means that the source size is can be of the order of C times W, provided that there is no ultra-relativistic motion. Remember that in that case you have gamma square factors which are coming into play. So provided there is no ultra-relativistic motion of the source of radiation, essentially, if the source is responsible of pulses which are observed as short as a few milliseconds, you can roughly estimate the size of the source just due to the causality-based argument that I was mentioning some lectures ago. So, given that the size of the source is C times W, so the area of the source projected perpendicularly to the line of sight is of the order of all this guys squared. So the area of the projected source over d squared is omega s. Well, this formula here is particularly handy because if you think for a moment, assuming that you know the distance of the sources that you are considering, you measure directly the intensity as a function of quantities that are measured. So the flux density is something that you measure, as well as the duration of the pulse, W. In particular, if you replace this estimate for the specific intensity in here, and then you invert the relation and you obtain the brightness temperature, you directly measure the brightness temperature of the source, which lies at distance d, which gives you for which you measure a flux density as nu, and which gives you a pulse. You are measuring at frequency nu, which is the frequency that you have here, and the pulse emitted by the source has a duration of W. So if you imagine you consider this given plot in which the x-axis is the product. You see here you have the product of nu times W. So nu you can measure in gigahertz, and W you can measure in seconds. So here is just the product nu W, so frequency at which you observe times the duration of the pulse, measured in units of gigahertz times a second. And in the y-axis, you put what lies here above. So the product of the specific flux, what you measure in Jansky, and distance. Typically for galactic sources, the distance can be measured in kiloparsec, so kiloparsec squared, because the distance is squared. You see that this is a log plot, because you see that decades have the same size. But you see, if you fix temperature, the brightness temperature, you immediately see that there is a parallel relation. This guy is, so what you have on the y-axis scales proportionally to what you have on the x-axis squared. So there's a power law with index 2 dependence. But the power law in a log-log plot is a straight line. So it means that all the regions having a fixed brightness temperature are described by all these lines. And you see that if you consider different values of brightness temperature, you are considering just lines which are parallel with each other, but which have a different offset in the y-axis. Because why? Well, this is a log-log plot. If you work out, if you put this guy here on the other side of the equation and you work out the logarithm of both sides of the equation, you see that times TB means plus logarithm of temperature. So it's just an offset in the y-axis. So it means that all these regions having line on the same straight line, they are characterized by having the same brightness temperature. And indeed, if you calculate here, all these numbers that you see in the top of this figure are the corresponding brightness temperature for the corresponding associated line. So all the sources lying on the same line have the same brightness temperature. Okay, so you immediately see that if you place the sources you are interested in this plot, you see something very interesting. You immediately see graphically the brightness temperature. And why is this so important in order to understand the process? Well, you remember that there is a limiting value for brightness temperature, in particular, which was the so-called Compton limit. If you remember, it was 10 to 12 Kelvin. So if you have a incoherent process, so for example, process in which the radiation is just due to different atoms which are work independently of one another. Think of a black body, for example. It means that for a given size, you remember, just for the limit that we saw at the time, for a source with a given temperature, a given size, the luminosity cannot overcome the luminosity of an associated black body with that temperature. So in that case, so getting back to the meaning of the brightness temperature, it means that in order to have an incoherent process, the brightness temperature cannot be larger, cannot overcome the Compton limit, 10 to 12 Kelvin. So it means that given that if you move from here to here, you are increasingly considering increasingly larger brightness temperature because the offset in the y-axis increases correspondingly. So it means that if you identify, as it is in this case, this very line is the line corresponding to the limiting temperature, this lines essentially divides this plane into regions. The gray one is characterized by brightness temperature below the limit. So in this region, incoherent processes are allowed, are possible. While the blue region here necessarily is characterized by brightness temperatures which are above. So there's no way you can have you can lie here through an incoherent process. So that's why the blue region is the coherent process region. And if you work out, so let's apply. So you see a lot of sources here. So many sources, the crab and all the other sources that I will mention, as well as the other. So you immediately see that as soon as you measure the distance of faster bursts, and nowadays we know the distance, or is just more or less 10 of them. Here, as I show you, just a line here and just one very famous one. But you immediately see, and as I wrote here, that the brightness temperature is extremely large, very large, 10 to 35 Kelvin. So this is a strong hint for a coherent process. So that means the process which is capable of just some degree of coherence in the radiation that you observe. So nothing like a black body, for example. And so this is another piece of evidence for the mechanisms responsible for these bright pulses. I didn't want to spend too much time on this, but let me just mention one of the sources which are thought to be one of the candidates which are thought to be responsible for fast radio bursts. And there's a lot of ongoing research about that. What are magnetars? Well, magnetars are neutron stars which are characterized by an exceptionally large magnetic field of the order of 10 to 14, 10 to 15 Gauss. And here I just show you a distribution of the magnetic field intensity for many classes of neutron stars, either belonging to binary systems or isolated. And so this is the distribution of the values. So depending on the class, you see, typical values are, so regardless of the specific kind of neutron star, you see that the magnetic fields at play are extremely large. So orders of magnitude larger than any possible magnetic field you can make in the lab. So typical values, you can have 10 to 8, but most of the bulk of them has around 10 to 12, as you might see. But there is a class, which is here, the red point, which is extreme of the extremes. You see? And this is just a closing of this distribution. This class of neutron stars has incredibly large magnetic fields between, as I said, 10 to 14, 10 to 15 Gauss. And because of that, they are called magnetars. It's just a shortening of magnetic stars. So stars, neutron stars, which are characterized by an exceptionally large magnetic field. And we study them by the fact that we discovered them essentially by studying their very active sources of X and gamma rays. We know a few dozens of this class belonging to our own galaxy. So by studying them, we learned that they are capable of undergoing periods in which they are very active. They emit pulses, not millisecond pulses, but a fraction of a 1 second pulses. And as I say, they undergo periods in which they are more likely to emit this X-ray bursts. Other periods which are more quiescent, they are not very. And essentially, we know that all this high energy activity, so all this emission of X and gamma rays are powered. So the question, who pays the bill? In this case, is the magnetic field. So you remember, you have a magnetic field, so the associated energy density scales with the magnetic field squared. So for such a large magnetic field, you have correspondingly larger source of energy, so energy reservoir. And indeed, this large energy reservoir associated with the magnetic field is powering for this activity. And occasionally, very rarely, these sources are characterized by very, very bright, very energetic, so-called flares, giant because they are so bright, they are so energetic that they're called giant flares. They can rarely occur. So far, we just observed 2, 3 of them from all the entire class, and none of them has been seen to repeat these giant flares. So they can, the total energy release is 10 to 46 ergs, and with a luminosity which is 10 to 47 ergs per second, which can rival, which goes beyond even the luminosity of a supernova. And if you think that the luminosity of the sun is kind of 10 to 33 ergs per second, so 4 times 10 to 33, you immediately see that at the peak of these guys are 10 to 14 more energetic, more luminous than the sun. So something which is really mind-boggling. And they are also very important because we believe that one way to form these sources is with a core collapse of a of massive stars that are also capable of making gamma ray bursts. But this is another story. If you want to know more about what is going on about magnetars, so for example, about the way people estimate the magnetic fields of the sources, the way we can study the activity of the sources and why we believe these sources connect with faster bursts. The course on multi-messenger astrophysics will deal fairly will devote quite some time to faster the burst. So there's a lot of things that I didn't tell you here, but just to let you be aware of the importance of this phenomenon, which has been attracting so much interest in the latest years, and in a connected way also this peculiar class of neutron stars, which are called magnetars, which are attracting a lot of interest. They have been the focus of many studies for many years prior to the discovery also of faster burst. But then, particularly in this very year, 2020, there was a major discovery about the possible connection between magnetars and faster bursts. Of course, given that faster bursts are extragalactic sources, because of the reasons that I told you, I didn't tell you then in the end the final evidence that proved that at least for 10 of them do belong to our to faraway galaxies in the universe, and we identify these galaxies. Again, as I said, this is something that I will discuss in the other course. But so the so-called smoking gun evidence. So the evidence based on which there is no question you found the distance, you measured the distance one specific faster burst. In our case, the lines of evidence that I commented here is just collective. I just showed you that you have different properties in terms of scattering pulse. You have an excess in dispersion measure, and all these properties that point to an extragalactic origin. And indeed, as I was telling you, we now know that some of them are really, really far away, because just telling you that they are extragalactic sources is not giving you very much information, in the sense that extragalactic source can belong to a galaxy which lie just a few megaparsec away from us. But you realize that a few megaparsec away from us is something, a few gigaparsec, so 1,000 further, is something different. And indeed, I can tell you that indeed faster sources are gigaparsec away from us. So not only are they interested, and you realize that given that the radio flux is so bright, and we are talking about sources which lie far away in the universe, it means that the energy released intrinsically is correspondingly large. So what is the source responsible of emitting such a huge amount of energy within just a few milliseconds? That's a big question. We think that magnetars have something to do with it, but we still don't know. So essentially, if I should I ask anyone a question, what are the sources of fast radio bursts? The correct answer is we don't know yet. But possibly that magnetars are a good candidate, but nothing can be said more. And so this is just a pictorial view of magnetars. So magnetars which are characterized, as I said, by a huge magnetic field. Here you see the structure is just a dipole structure of the magnetic field. We think that magnetars have a much more complex structure of the magnetic field. But anyway, this is just a way of graphically illustrate the road. And essentially, that is it. So this exhausts all what I wanted to say about faster burst. If you want to know more about this, as I said, this is a very hot topic. So here in the bottom, I just put a list of review papers. On them, I just put the most recent one, because things are changing so fast that it's advisable just to take the most recent papers. In particular, a few 1 month ago was published also this one here on Nature. So you see that Nature is one of the probably two most important journals in any field, nature and science. So it means it's evidence that indeed these topics have been really important. And in the top, I just put essentially about the general physics behind behind the way electromagnetic waves are affected in crossing plasma regions. So the textbook, and again, the Rybicki-Leitman is my favorite one, also in the scale, but also the Longueur. And also for the scattering part, I used the Thomson Moran Svensson, very useful, in addition to the other one. But the first three are the ones which I mostly took for this topic. So this is all for this. And okay, so now let's start with a new one, which is, as I said, the last one. So, last but not least, so what is this topic? Well, this is about mechanisms responsible for accelerating particles to high energy. And in particular, we will consider, I immediately tell you that this is a very complex topic, very complex. And again, this is one of the topics that are currently, so there are very important lines of research devoted. So there are researchers which devote their entire career to the study through both from a theoretical point of view and also through some complex simulations in order to reproduce how acceleration of particles to very high energy works in the universe. And the first person that addressed the problem with some very good insights was Enrico Fermi, who devised kind of two mechanisms. In particular, we will see, and they are called the Fermi mechanisms. So mechanisms that we will see, which can explain how particles can be accelerated up to relatively high energies. And they are called first order or second order. This is referring to the way energy is increased, the relative energy is increased per scattering in orders of